Webinar on on-demand vertical and 3D topographic differencing. And want to thank Chelsea Scott and Chris Crosby, who are here with me. I'm Ramon Aerosmith, and I'm just here to get things started. I think we'll hand things over to Chris, who will then hand it off to Chelsea, who's going to run the most of the webinar. So please take it away, Chris.
Thanks, Ramon. Yeah, so my name is Chris Crosby. I'm at UNAVCO in Boulder, and I'm a co-PI of OpenTopography, along with Ramon and some other folks on this call, Vishy Nandigam's the other PI at San Diego. So before we begin, just a couple of logistics. Thanks to Melissa Weber, who's helping to run this webinar and coordinating everything, and she's also recording this webinar. So this will be available on the OpenTopography section under kind of online training. We have a webinar. We've started a webinar archive. So feel free to pass this recording on to colleagues who weren't able to make it, or you'll be able to revisit if you want to kind of rework through some of the things that Chelsea's going to show you. Please use the Q&A function to ask questions. And Ramon, Chelsea, myself, Matt Beckley is also in the OpenTopography team, and Vishu, I think, are all on this call. So we will try to answer those questions, especially if they're quick. If there are things that sort of need more discussion, we may save them for till the end of the webinar, where we can have a bit more discussion. And so we do have 10 to 15 minutes for discussion at the end. But I know at least Chelsea and I are willing to stick around longer if people want to keep chatting beyond that 1 hour mark. But we'll try to sort of wrap up the formal webinar by the top of the next hour. Chelsea, yep. So we're going to do a quick introduction to OpenTopography. I'll do that just because we had over 300 people sign up for this webinar. And looking at the list, I know some of you are very familiar with OpenTopography, but some of you may not be. So we'll do a very, very quick intro to OpenTopo. And then I'll hand it off to Chelsea, who will go through vertical differencing and then a demonstration of those tools within OpenTopography. And then she'll talk a bit more about 3D differencing. We'll look at some of the jobs that we ran, and then we'll go to discussion. So yeah, you can go to the next slide, Chelsea. So OpenTopography is a National Science Foundation funded project that was begun about a little over 10 years ago now to democratize online access to high resolution topography data. So this was begun focused on airborne Lidar topographic data, but more recently, we've started to do more work with photogrammetric data, both sort of space-based commercial satellite imagery, derived topography, as well as UAS collected data. And then we also offer access to a whole suite of kind of lower resolution data sets like SRTM that kind of provide global or near global coverage. And we've always emphasized access from the data, raw data sets, so that's things like point cloud products, through to processing tools to allow you to derive easier to use products that are more suited to sort of the end user. And so OpenTopography has this co-location of data and processing tools. And Chelsea's going to highlight the differencing tools today. So as I said, OpenTopography was funded in 2009. We are funded by the NSF EAR Geoinformatics program. And it's a small team, so everybody in that picture is who makes OpenTopography work. So I say just about everybody in that picture is on this call in some form, except for Min Fan, who's one of our software engineers. It's a small team. We like to get a lot done as much as we can. And I think one of the successes is that this collaboration between computing experts. So the lead institution is San Diego Supercomputer Center, which is at the University of California, San Diego. And then sort of the domain science, geospatial data people at UNAVCO and Ramon and Chelsea at Arizona State. So what do we do broadly? This is the online hosting and distribution of point cloud, raster, orthoimagery, and other kind of topographic data products. Go ahead. One of the things we've recently done, and we did a webinar about this in the fall, I guess in November. We now provide access to the whole suite of USGS 3D elevation product data sets. So if you're interested in that and you missed that webinar, it's recorded on the webinar archive in OpenTopography or on our YouTube channel. We have a history of doing lots of education and training. Mostly these were in-person short courses in everything from 1 day through to full week trainings in best practices in topographic data analysis, processing, and now we're starting to do these webinars in the age of COVID. And we work with a lot of collaborators. So the data in OpenTopography come primarily from the National Science Foundation, data sets collected for various types of scientific applications, but we have more recently grown our collaborations, and we now work with groups like Land Information New Zealand, which is the national mapping agency in New Zealand. They're using OpenTopography to distribute all the LiDAR collected as part of the nationwide LiDAR program in New Zealand. We've worked with various states like Indiana and Utah to host data, as well as tribes, a few small commercial entities. We have data sets from the Usgs and lots of other partners. And so OpenTopography is very much interested in growing that base of collaborations as well. And so, as I said at the very beginning, really the goal of OpenTopography is this ability to access data kind of at the tier of complexity that you are comfortable with or interested in or need for your science. So this is everything from bulk downloading of point cloud files and LAS to LAZ products all the way through to production of custom DEM products. And then we're growing out a suite of tools for various kinds of things. So we're going to talk about topographic differencing, which is an activity that Chelsea's been leading the charge on for the last 2 years or so. But we just recently released a tool to calculate canopy height models from topographic data products, and we have hydrologic flow routing and a bunch of other things. We're going to talk about basically the GUI, the user interface through the web today, but there are, just to make you aware, we do have APIs for accessing certain types of data, like all the global data sets are available via API, and then also kind of bulk downloads, so essentially pulling files straight off of a cloud-based file server for those of you who want kind of power access to data. I think that's it. Handing off to Chelsea now.
Great, thank you, Chris. Thank you for everyone for coming to today's webinar. I am very much looking forward to discussing the topographic differencing tools in OpenTopography that we've been adding over the past couple of years. So just to start off, what is topographic differencing? Well, it's a tool that uses high resolution topography data sets for observing and studying changes to the Earth's surface. In particular, we look at multitemporal data to detect this surface change. And today we'll be talking about 2 different applications or methods of differencing, and that's vertical and 3D differencing. And we'll show you how to use OpenTopography to perform this type of topographic differencing. This here on the right is an example of topographic differencing, looking at changes along a river and agricultural lands in New Zealand. So here is a map of data sets that are available from OpenTopography. The red are data sets that are hosted by OpenTopography. The green are open data from the Usgs 3D elevation program that are currently accessible to academics, US academics through OpenTopography. If you look at this map, you'll notice that there's quite a bit of overlap between these different data sets. And an exciting opportunity is to perform topographic differencing to measure how the landscape has changed over time between the first and second or subsequent acquisitions of the LiDAR data. And there's many applications for these types of results. For example, in natural hazards, urban development, forest structure, river erosion, to name a few. And I'll discuss some of these examples in more detail today. So there's essentially 3 flavors of topographic differencing that we've implemented into OpenTopography, and they're shown here. First is vertical differencing, where we start with point clouds. And this here is illustrated for sand dune migration in New Mexico. Second is vertical differencing, starting with rasters. And this shows the results of the Kilauea eruption in Hawaii. And 3D differencing, shown here for the Kumamoto earthquake, represent 3D change with these arrows and colors. So today we'll discuss all three of these types of differencing, starting with these two types of vertical differencing. So here's an example of how vertical differencing works. It's looking at sand dune migration at the White Sand Dunes National Monument in New Mexico. So we have two different topography data sets. The first is called the compare. In this case, it was collected in September 2009. And we see this picture of the sand dunes, and you can look at the topography and see that the sand dunes are moving to the northeast, driven by wind from the southwest. Here's a reference data set. This is the second data set that was acquired in June 2010. So we have these two data sets, we can perform topographic differencing, and the results are shown here on the right, where we see blue represents deposition or accumulation, in this case of sand, and red represents erosion. Based on this graph, we can again see that the sand dunes are migrating towards the northeast. So I'll discuss in a little bit more technical detail how this vertical differencing works. So again, we start with two data sets. It can often either be point cloud or raster. First data set is called the compare. Second is called the reference. And you'll see here, as is typically the case, that the compare data set has lower resolution and sometimes higher noise than the reference data set, which was acquired later. So an early step in the topographic differencing is to grid both the pre and post data sets to the same grid. So they need to have the same bounding box and the same resolution. Next step is to perform a raster difference or subtraction. So we take the reference and then subtract the compare. The result could look like this. We see blue shows upward motion of the ground surface, and red shows downward motion. And in OpenTopography, we've added the option of masking out displacements that are below an error threshold. So here we see these gray points represent very low displacements that the user said were going to be below the noise threshold from the data sets. So here I'll discuss the workflow that we've developed for topographic differencing. So a requirement for performing topographic differencing is that both data sets overlap. So they must cover the same area. The next step in the processing is to put both data sets on identical grids. We can work with data that are originally point cloud or raster data sets. And we expect that the data sets have varying raster or point intensity. In other words, different resolution. The next step is to perform a raster subtraction. We can then integrate a user-defined error threshold. And as you'll see, that is an option to provide for the on-demand differencing in OpenTopography. And finally, once the differencing job completes, then the user can see a display of the differencing maps as well as histograms of the differences. So here's an example of topographic differencing results for the Kumamoto earthquake in Japan. And you'll see a few faults highlighted in these locations. You also see that this house here is red. Fortunately, this means that the house fell or was highly damaged during the earthquake, but this plot does show that we can use topographic differencing to characterize damage from earthquakes. So what are the challenges and requirements for topographic differencing? So legacy data sets are older data sets that typically have lower spatial resolution and higher noise than modern data sets. But these data sets are very much invaluable following an event of interest because they're often the only representation we have of the Earth's surface before the event. Metadata is very important. For example, it's critical to know what is the coordinate system of the data set. In the topographic differencing, we've implemented differencing of hybrid data. So hybrid data are data sets with very different characteristics, such as point density, or different data types, such as structure for motion and Lidar data. So initially, we implemented differencing with point cloud and raster data that could have varying point density. Currently, we're working on adding differencing for terrestrial laser scanning, structure for motion, global raster data. I believe we currently have at least one example of Lidar to structure for motion differencing on OpenTopography. So the algorithms that we develop must work on demand with data sets of different types. So they need to be able to work essentially without failure for whatever data we ingest in OpenTopography. And the cyber infrastructure system that we develop must be able to interact with the high performance computing system that OpenTopography operates on at San Diego Supercomputer Center. So I'll now go over a few examples of topographic differencing. This example shows Salt Lake City Airport, differencing Lidar data between 2011 and 2013. And you see these blue and red airplanes. So the red airplanes represent where airplanes were parked on the first date, and then the blue represents locations where earthquakes were parked at the later date. This is a very just cool example of topographic differencing. Here's an example showing the 2019 Ridgecrest Earthquake in California. See these two hillshades. The second one, you see topographic fault scarp goes right here. And then in the colored plot, you see the change in surface elevation from the earthquake. This an example is from satellite-based stereo imagery that was collected in both 2016 and 2019. Here's an example of rock falls in Yosemite National Park in California. See several red areas here and here, for example, where we had large tree and rock falls between 2006 and 2010. These rock falls do pose significant hazard in Yosemite National Park, and topographic differencing is an important tool for determining the location of these rock falls. This is looking at the Calhoun Critical Observatory in South Carolina. This critical observatory was set up to understand how does land that had extensive agriculture and water degradation recover over time, and showing the differences in the digital surface model between a summer date and a winter date. We've also implemented topographic differencing of digital surface and digital terrain models. This is looking at the Christina Critical Observatory just outside of Philadelphia. And here you can see we're subtracting the digital surface model from the summer with the digital terrain model from the spring. So this is one way of approximately characterizing the height of vegetation during the summer. So a question you may be asking right now, Chelsea, this is cool. How can I do this on OpenTopography? Well, we're about to show you. So currently we have topographic differencing implemented on 60 dataset pairs. And these datasets cover a wide range of geologic and anthropogenic processes. So here I've highlighted a few examples, to include Salt Lake City, which shows a lot of very interesting examples of anthropogenic change to an urban landscape. We have topographic differencing implemented on a number of critical zone observatories, also on many rivers and riparian zones. Topographic differencing is added to look at many different types of natural hazards, including landslides, rockfalls, volcanic eruptions, and earthquakes. And of course, as the OpenTopography data set or data archive continues to grow, there'll be more and more examples. So today we invite you, we're going to go over a demo. I'll show you how you can perform topographic differencing on OpenTopography. Here are some nice examples that you may be interested in looking at. So for example, urban growth, Salt Lake City, leaf on to leaf off in central Pennsylvania, riparian zones, volcanic eruptions, rockfalls, earthquakes. In a few minutes, we'll discuss 3D differencing. Here are some nice examples. So we do have over 100 people on the webinar today, which is very exciting. However, our system was not designed to have 100+ people press go all at the same time, especially processing the maximum size data set. So we invite you certainly to follow along with us today. If you would like to process a data set during the webinar, we ask you to please do only a vertical differencing data set and limit yourself to either 3 square kilometers if you're looking at raster, or 3 million points with point cloud. And this is just so that the data sets process fairly efficiently during the webinar. And please do not run 3D differencing. This is a little bit more computationally intensive. But we do invite you to perform differencing using maximum data set size that we allow anytime after the webinar, when we don't expect to have 100 people all initiating jobs within a few minutes of each other. So I will go over how to do differencing on OpenTopography. So you'll want to go to opentopography.org. Maybe Chris or Ramon, you could put that link into the chat. So then that should take you here to opentopography.org. And then to start performing differencing, you should click here to go to data. So then take you to the web page where you can see all of the data sets that are either hosted or available through OpenTopography. Many of our data sets are in the US, but we do have some data sets, including some with very interesting differencing examples internationally. Particularly, I would invite you later to check out New Zealand. Today, for this demo, we are going to go to Hawaii. So you can zoom in to Hawaii down here. You can see you have all these data sets that are hosted by OpenTopography. So go here, say select a region, and find an area where you see overlapping data sets. So where there's several of these red lines on top of each other. So let's go here, for example. So that brings you down here. You can see the data sets that we host over the area that you selected. So this includes 2 Kilauea volcano data sets, one from July 2018, one from June 2018, and then the Hawaii Big Island survey. And you can see these two top data sets have differencing, and all the data sets have point cloud and raster options. So today, to perform differencing, we want to click this differencing tool button. So that will then take you to this page. I actually should say it doesn't matter which of these differencing options you select. Ultimately, perform differencing with both data sets. So it takes you to this page, says Topographic Differencing. And you can see there's 3 differencing options, and that's because this data set exists in both point cloud and raster form. So we can do vertical differencing, start with raster, vertical differencing, start with point cloud, or 3D differencing, which will by default use the point cloud option. So today we're going to do vertical differencing starting with raster. This is the least computationally intense way of differencing. And incidentally, we let you process with larger data sets because of this. So I would always suggest doing start with raster vertical differencing if this option is available. So you can click start with differencing, start differencing. So then it takes you to this vertical raster differencing page. You can see the data set, Kilauea volcano, Hawaii, that we originally started with. So here is an example, or you can see the 2 data sets that are available over this area. We have the Kilauea volcano July 2018 acquisition. This is the reference for the second data set, which is shown in purple. And then the green data set is the compare data set from June 2018. So it was acquired first. So to perform differencing, we want to come here, say select a region, and then put a box over the region that we are interested in looking at. And so you can then scroll down and look at some options. First is to switch the reference and compare data sets. So when we click or unclick this box, you'll see that the July and June text changes. So ultimately, clicking or unclicking this box will change the sign of the differencing product. Another option you have is grid resolution. So this will be the resolution of the digital elevation or DEM model that is made for the differencing. We provide you a suggestion, which is based on the resolution of the raster data set. So for many data sets, the suggested resolution will be 1 meter. If the data set, say, older and has much lower resolution, then you may see that the suggested grid resolution is larger, say 2 or 3 meters. And you can, of course, change this, but we suggest that particularly when you're starting out, you do keep the suggestions that we make. So in this next box, you have coordinates. So you can either draw the box to select the area where you want to perform differencing, or you can manually enter the area here. Most users find that it's easiest to just draw the box as we had done earlier. And you see here, it says the selection area is approximately 2 kilometers squared. So since we're looking today, right now, to process 3 kilometers or less, then we can confirm that this is a good value. Layer types, sometimes you'll see that for the data set that you pick, there's both a digital terrain model and a digital surface model that is available. In that case, you can choose to perform differencing with different combinations of the DTM and DSM. For this data set, only the DTM is available, so that is the only option. there's here option to define error threshold. So you can click that, and the default option, which we'll keep, is 0.5 meter. For many data sets, this is probably a little bit big, but it does have a very intuitive understanding to many users. So that is why we set it to be 0.5 meter. But we do invite you to process differencing with different options and see how the results are impacted. This final toolbar is for visualization. And so the default is to create topographic hillshades from the DMs from both the reference and compared data sets. And we suggest that you leave this button clicked. So finally, you can enter a job description. So job title, call this OT differencing demo. You can add a more extensive job description if you would like. You have option of, if you're logged into OpenTopography, your email will automatically appear here. It can be logged in if you've already made a free account, which we recommend that you do. If you have not made a free account, you do have to enter your email. And then we can press submit. And when it finishes processing, you will receive an email from OpenTopography that will send you a link for how to find your processed jobs. So when you make it to the end of this page, you can press submit. So that will then take you to this page where you can monitor your job as it's being processed. You can also close this window and check your email in a few minutes, where you will get a link to take you back to OpenTopography to get the results of the topographic differencing. So that is our demo. We're now going to go back to the PowerPoint presentation, and I will discuss 3D topographic differencing, and then afterwards we will review the results from the job that we just started processing. Just project this. Okay, so 3D topographic differencing. This is the final or most recent differencing capability that we added to OpenTopography. This here is an example showing 3D differencing results from the 2016 Kumamoto earthquake in Japan. You can see the vertical displacements are shown in with these colored circles, and the horizontal are shown in arrows with ellipses that represent the error in the displacements. This approach was initially very exciting, along with the 3D with the vertical differencing, because it could be used to resolve deformation along and adjacent to active faults in locations where other geodetic data sets, such as INSAR and GPS, often lose spatial resolution. So 3D differencing is done with a windowed implementation of the iterative closest point algorithm. And I'll use the next few slides to discuss this algorithm. So we start with a subset of both Lidar data sets. Here you can see the compare is shown in blue and the reference is shown in red. And the size of the window is typically about 50 meters or so. And the reference window is always a little bit bigger so that the deformed compare window fits within the reference window. And that might make a little bit more sense when you look here, this animation where you can see that the blue or pre-data set is iteratively moving closer and being better aligned with the post data set. And this alignment is done with the iterative closest point algorithm. So the alignment is done with a rigid deformation. So we take the undeformed point cloud, apply a rotation, and then translation. And this generates the deformed point cloud. These steps are summarized here. We again start with a windowed subset of both the compare and reference data. You can see here, two data sets are not aligned. So we then use the iterative closest point, or ICP algorithm, to find the best rigid deformation to align these two data sets. And once we do that for windows that cover the entire data set, can then generate a 3D displacement field represented by the horizontal and vertical displacements. Often also generate a rotation field, although that is not shown here. So here are the steps that we use to implement the 3D differencing into OpenTopography. In the first step, the user must decide that they want to perform 3D differencing. And so they must select a region with overlapping data sets and then choose to perform 3D differencing. User is given several options in the processing. And one of the more important options is this window size. And so again, that is the size of the compare window that is taken of each data set. And I'll discuss how we make suggestions of the best window size to use based on data set metadata. Next step is to calculate 3D change. This is done again with a windowed implementation of the ICP algorithm. In OpenTopography, we use LAST tools to perform the windowing. And then finally, after the job has completed, the user is presented with both geotiffs and graphics that show the results of the 3D displacements and rotations that are used to best align the two data sets. And so in the next few slides, I'll discuss how we've optimized the window size as well as the algorithm choice. So this is looking at optimizing the window size, which we do based on synthetic testing. So we take many data sets that are hosted by OpenTopography, split them in half, and offset one of them. We know the offset, and then we use the ICP algorithm to recalculate the offset, synthetic offset that we imposed in the data set. And we then characterize or quantify how well we are able to retrieve the input displacements. So this plot here shows displacement error versus window size. This is for the Indiana data set acquired in 2012 with a point density of about 0.5 point per meter squared. And these different colors are showing in blue and red the horizontal displacements, and in black the vertical displacements. And you can see in this case that the error does decrease with increasing window size. And this makes sense. With larger window size, essentially have more data that can be used for the alignment. So we do expect lower error. This blue line here is the 20 centimeter error threshold. So we decided that really to perform topographic differencing, we would like most displacements to have this error less than or equal to 20 centimeters. And for this older Indiana data set, we never had the error pass below this error threshold for window sizes up to 250 meters. In contrast, this is on the right, looking at the Utah data set, much higher point density, and we see that at about 20 to 25 meters, the error does go beneath this error threshold. And so for this Utah data set, we would define the ideal error or window size as about 20 meters. So we applied this same analysis to many data sets hosted by OpenTopography. And the results are shown here, looking at the ideal window size versus point density for all of these data sets, which were sometimes synthetically thinned. And then we use this equation, which is best fit exponential equation to this data set to make suggestions of the ideal window size for performing differencing on OpenTopography. You can see here, once we're about larger than 2, or once we have more than 2 points per meter squared, then the ideal window size is about 40 meters. And for lower point densities, the ideal window size is larger and follows this approximately exponential curve. So in OpenTopography, when you see a suggested window size, it does come from this equation. The other aspect we looked at was what is the best algorithm to use for the 3D differencing. There's two different ICP algorithms. First is point to plane, and this aligns compare points and to the reference surface. And there's also the point to point, which aligns compare and reference points. So we went in with the assumption, looking at the Kumamoto earthquake, that we wanted to see differences or sharp changes in displacement along the faults, but not along flight lines or along changes in landscape type, for example, from the agricultural fields to the more forested and urbanized landscapes. So here we compare 3 different algorithms: LibICP point to plane, LibICP point to point, and the Poodle point to point algorithm. And our preferred algorithm that we implement in OpenTopography is this point to plane algorithm. And that's because we see that these sharp changes in displacement are largely localized to these black lines, which represent the faults that ruptured during the earthquake. So now go over several examples of 3D differencing results. This is looking at the Slumgolian landslide in Colorado. And here we performed differencing from Lidar data that was acquired about a week apart along this creeping landslide. And so here in the hillshade, you can see the location of the landslide. And then the differencing results capture the horizontal and vertical creep motion of the landslide over the week-long period. Here's an example from the magnitude 7 Kumamoto earthquake in Japan. So you can see sharp changes in both the horizontal and vertical displacements across several faults that ruptured during the earthquake. And finally, we're back to the sand dune migration example, where before we showed both the hillshade and the vertical differencing that suggested motion towards the northeast. This plot here does again show, on average, sand dune migration towards the northeast. This is an important example. Typically, we apply vertical differencing to examples where we have rigid deformation or movement of the Earth's surface. Of course, that doesn't really apply to sand dune migration. However, over time, the sand dunes do approximately maintain their shape. And so therefore, we can apply 3D differencing to sand dunes, which is a little bit noisy, but does capture the overall sense of motion that we would expect from both the topography and the vertical differencing. So I wanted to point you towards this paper that I've been referencing, particularly for the 3D differencing aspects of this talk. Title of the paper is Measuring Change Along the Earth's Surface, On-Demand Vertical and 3D Topographic Differencing, hosted by OpenTopography. This is currently in press as a software contribution at Geosphere. So I invite you to keep your eyes peeled for this paper. If you would like to learn about what we were doing to implement differencing in more detail. So we will now review the data that you possibly processed. I would also like to point you towards this page that we made on OpenTopography, where we list differencing resources, including blog posts with differencing examples, several talks that we've given at different presentations, and GitHub links to the software that we wrote to implement differencing in OpenTopography. And then I'll be happy to take any questions. So you can go, you left the page open. If you'd processed any of the results, they either should now or soon be finished processing. So this is the differencing job results. Again, you can get this page in your email. So you can see here, we have reference and compare data sets. You can see the job took just over 200 seconds to complete. So long enough to get a coffee, but not too much longer. Probably the job would go faster if you're running not during a demo. So here are the products that you can download. You can download the topography of the reference and compare data sets, as well as the raster differencing results. Here are the, is a differencing plot, again, showing the same color scale as we talked about before. And then this plot is showing a histogram of differencing results. So it's counts versus vertical difference. And then these later plots are showing the results given the error, half a meter error threshold. So points below that threshold are plotted in black. And then here's the histogram of that result with those points that were masked out by the error threshold that now have been removed. And just sometimes convince yourself that the landscape did in fact change. We present both the reference and compare data sets.
All right, well, shall we give Chelsea a hand? Sorry, I interrupted. Go ahead, Chelsea.
Just want to say thank you for coming to our webinar today. We'd like to invite you to get in touch with OpenTopography on our different social media platforms, including Twitter, Facebook, and Instagram. If you have any questions about OpenTopography in general, or particular things during this presentation, please get in touch with us either at info@opentopography.org, or you can feel free to contact me directly with my email here. And we invite you to please complete this feedback form and tell us what you thought about today's webinar. And with that, thank you. And we're happy to take any questions that you may have.
Okay, now let's give Chelsea a hand. Sorry, I jumped the gun there. And I want to just definitely thank Chelsea's leadership on this. She's really been the intellectual leader of this work. Thank you so much for pushing it forward. We've had a number of questions as the webinar went along, and Chris and I tried to address some of them as we went. Let me see. Yeah. Okay. The quick thing. There's a question. Maybe can one of you guys paste the feedback form into the chat so people can click on it?
I did.
Oh, okay. Sorry. Maybe Andy Newman.
Yeah, I think maybe Andy and I were help. I posted there it is again.
Okay, great. Maybe I'll just call out a couple of questions, if that's okay. One, let's start with Chelsea. You were just showing the results from the Kilauea vertical differencing, and Annie Berlingeri, sorry if I didn't pronounce your name correctly, asks, can you describe how error is incorporated in more detail? Is that just a single value threshold applied to the entire data set? And so I said, yes, but do you want to talk about how, I mean, it's totally arbitrary in our system, right? There's no
So currently, yes,
calculation.
It's completely arbitrary. The points that are masked out are those whose absolute value is smaller than the error threshold that you implemented. Long term, we were able to get quality metadata with errors for individual data sets, then we could think about implementing error calculation that was a little bit more advanced and built in the data set or metadata. But we do invite you to look at changing that 0.5 value to something that you think may better represent the data sets that you are using.
Yeah, I was just going to say that for basically not every data set in OpenTopography, for the vast majority, there's a link above that data access map that has a link to the metadata for each data set. And so you could dig into the data set and look at the reported, like say, vertical accuracies for a given data set, and then use those to refine your error estimates. Like ultimately, it'd be great for OpenTopo to go back through the hundreds of data sets that are in our system and harvest that information and populate it as a metadata element so we could more accurately inform that error threshold. But at the moment, that's a task that we haven't undertaken yet.
Yeah, I mean, the beauty is it's OT compute resources, so just try it a whole bunch of times and sort of use it to sort of heuristically to explore what might be an appropriate value based on other information you might be able to gather. We had a question from Eric Barefoot, says, does the 3D ICP algorithm allow you to choose true points to constrain the deformation if you want? For example, if you have a monument surveyed with RTK GPS or something.
Does that let you select true points?
I guess maybe zero error reference points. It's probably more a question about sort of alignment of point clouds.
So we don't let you edit the alignment. And if the two data sets are offset from each other or misaligned, then you would see an extra value in the displacement fields that represent that net offset.
Right. Let's see. Yeah, points with a known offset, kind of what he's thinking. Yeah. So it.
But again, you could, you know, if you think you have an area with zero deformation in the far field, and you find a non-zero deformation in that area, then you could use that and subtract from the whole differencing plot.
Yeah. Let me just keep going. Another question we have is from Ed Nissen, one of our sort of people who've inspired us and really led this 3D differencing early. So thanks, Ed, for being here and all that you've done for us. Ed asks, have you noticed any systematic difference in the quality of ICP results from using full point clouds versus classified ground returns?
The short answer is it depends. If it's a case for Kumamoto, where there's very, very few points that are considered ground or classified as ground, the ICP will not work if you don't use the whole data set. But in cases, for example, where I've worked in California, if you're doing Lidar and structure for motion differencing, in that case, the results are better with just ground points because those two data types characterize or measure the vegetation very differently. And so it's helpful to be able to remove the vegetation.
Right. Thank you. Now we have two questions, a couple questions maybe related about how, well, okay, let's see. The first one, how often are new data sets added?
Yeah, this is sort of, there's like several questions in here, but they're basically about like, you know, can I process my own data? How do new data sets get in? Questions about vertical differencing on 3-depth or differencing on 3-depth USGS 3-depth data sets. So the answer about data sets getting added, it's sporadic. It depends on sort of who we're working with at the time. Say, for example, New Zealand sends us, you know, between say 10 and 20 new data sets a year. And so that's a growing archive. We get data from the National Center for Airborne Laser Mapping, usually say 6 to 10 data sets a year. It just has to do with when they come in. The data, if there's data out there that's not in OpenTopography, but you'd like to be able to difference it, I did post in the chat links to software. So basically a lot of the underlying code that's running in the OpenTopography web interface, we've posted on GitHub. And so you could download that code and get it running on your own data sets. And that's probably something to if you're really interested in exploring these tools, and especially doing it at scale or doing with lots of different kinds of data sets, there may be a reason to just familiarize with yourself with those codes. 3-depth is definitely something we'd like to do. The 3-depth data are a little bit challenging because the vertical datums are not all the same. And in some cases, the metadata is not particularly good on those data sets. And so we would basically have to resolve some of the vertical datum issues. And either transform them on the fly or some other solution. So there's some technical, devil in the details issues associated with getting this working on 3-depth, but it's definitely in our list of things to tackle.
Yeah, I should add that we do enable people with academic accounts or EDU email addresses to process those 3-depth data. So at least some people can get them and download them and then do some desktop work, but it is
exactly
challenging.
Yeah, and I guess that's another
on-demand differencing for those data sets yet.
Yeah, not on-demand differencing, but certainly you could get the data from OpenTopo and then apply the tools that we provide offline, to do. Yeah.
Let's see. Go ahead. Zach Hilgendorf asks, does OT have a suggested calculation for the error threshold? I guess this is the vertical differencing. Maybe Chelsea, do you want to talk a little bit about the error threshold?
So if you want to do it very simply and you know the error in each data set, then take essentially the square norm of both of your data sets, the error in both of your data sets to calculate at least a very rough error to implement for the vertical differencing.
Okay, good. And then just while we're working on Zach, another question, and then we'll come to T. Carlin, is for people who want to add TLS, UAS data sets to OT that could be differenced, is there a preference for uploads, point cloud, raster, both? Chris, do you want to take that one?
Yeah, I'll take that one. So generally, as a general rule, we prefer to receive all the data products associated with the data set. So if you have both point cloud and raster products, we prefer to archive those, as well as like, good metadata and all those kinds of things. So that's a kind of the default answer. But the subtlety here is that there's basically two ways to get data into OpenTopography at the moment. One is for larger data sets, we get them either via file transfer or hard drive, and then we upload them through kind of into the workflow. So the 60 some odd data set pairs that Chelsea showed you are all of that class. We do have, as Ramon just posted in the chat, this thing we call the OpenTopography community data space, which is meant to be a user-oriented upload tool. So for smaller data sets, TLS and UAS, SFM type data sets may be the kind of thing we're thinking about here, where you basically request a permission to upload your data, and then you kind of drag and drop into our interface, and we ingest the data and extract as much metadata as we can, and then you provide some additional descriptive info, and then data get published into our archive and receive a DOI. And so this is primarily oriented towards data publication for kind of fair data best practices associated with like paper publication at the moment. Data sets that are in the community data space are not enabled for any kind of downstream processing at the moment. And so if you did add data through the community data space, they wouldn't be available to process. However, that is also on our list of things to do, is to add all the full suite of OpenTopo processing tools on top of the community data space data sets. And so that's definitely another one that's like in the queue of things to get done. Again, it also has a suite of technical complexities that we're working on.
Yeah, one editorial comment is just, you may see, well, why is it so difficult? But these, what I've learned, even though I'm inside of OpenTopo, is the challenge of production. It's a lot harder to do something when you want it to work for people when they come into the web interface, and so that's why it may seem a little bit limited, but that's, as Chelsea explained, why some of the pre-computing of suggested error window, suggested processing windows, for example, has to be done, and keeping things robust, which is a little bit different than running it on your own desktop. Chris, here's another question for you. Apologies, as this might not be completely germane, but do we have a sense of when OT's data democratization process is going to overflow the banks of academia and into other sectors, specifically government? These tools seem awesome, but their application is extremely limited beyond academia, given the lack of access to the tools.
Yeah, so everything Chelsea showed you today in this demo is open to anybody who wants to do so. There's no restrictions currently on the processing tools. For topographic differencing, there is the only place that there's a restriction in access at the moment is this USGS 3DEP data, which is this vast, 65% of the United States that we're accessing in a slightly different way than we do with the rest of data in OpenTopo. And we have at the moment imposed a restriction to US academics. And so, but those tools, as we just said, aren't available for differencing anyway. So they're not really, it's not particularly germane to the differencing discussion, but it is relevant to the broader question that was asked. We're working on a way to make all of the USGS 3DEP data available to anybody who wants to access them through OpenTopography. But at the moment, those kind of value-added services sitting on top of OpenTopo are restricted. And it's a question of a little bit of politics. It's a function of resource levels and funding. If you're interested in this topic, we talk a little bit more about it in the webinar we did in November specifically on 3DEP. And I can post the webinar archive link in the chat here in a second once I find it. But everything that Chelsea showed you today, you can do, anybody can do. Doesn't matter who you are or where you come from. In fact, you can run differencing jobs, I think, without even having an OpenTopo account. Is that correct?
That's right.
Yeah, so you can even run as a guest. You don't even have to create an OpenTopo account. So, so that's the.
Excellent. All right. Well, it's 5 minutes after the hour, so we've gone the full hour. So we may want to bring this officially to a close. But any urgent final chat items or remarks?
I just posted a link to the YouTube recording of the 3DEP webinar for people who are interested in that topic and want to. I would encourage you to if you're interested in 3DEP and especially in some of these issues about restrictions, I'd encourage you to watch that because we did tackle this a little bit.
Yeah. All right, well, let's give a hand again to Chelsea and Chris. Thanks for your guys' input, and a hand to all of our attendees. We had as many as 104 today, so that's really, really great. A lot of enthusiasts out there, so don't be strangers. Please keep in touch with us. We appreciate everyone as the Open Topography community. So let's maybe end things officially. Chris and Chelsea, you want to say a few final remarks?
I was going to say thanks to Melissa, who's out there as UNAVCO, so behind the UNAVCO services user there on the screen, who's keeping this whole thing running and making the recording. Once Melissa's got that recording finished and we've uploaded it to YouTube, we'll post it on that webinars archive. And maybe, I think Chelsea, last time we sent you
a link to the webinar recording as well.
Yeah, so anybody who signed up for the webinar, even if you didn't participate, we'll send you an email at some point in the next week or so with that link to the webinar recording.
Yep. All right, well, let's we can end it formally, but maybe if people have a few more questions, we can stick around.